Now, the last few sections have been very mathematical, but Le Chatelier's principle, it describes conceptually what happens. We come again back to our hydrogen plus nitrogen to make ammonia, and first direct your eyes at the part called initial equilibrium. We are measuring how much is there by partial pressure. You see green corresponds to H2, red corresponds to NH3, and blue corresponds to nitrogen. What's going to happen is in section number 2, more hydrogen is going to be added. Well, reaction is going to occur. And we will wait until equilibrium is reestablished, which is section number 3. So this section is here to say to you, an equilibrium constant is a constant. We can start out with a certain set of conditions. If we add another participant in the equation, we will come with a new set of conditions, but that equilibrium value, magnitude, will always be a constant number. So if a system is at equilibrium and it's disturbed by a change in either temperature, pressure, and or concentration, the system is going to shift its equilibrium position to counteract the effect of disturbance. Now, if we were in class, I'd be making a joke. I'd be walking up to somebody and say, if I punched you in the face, what would you do? Usually get some laughs. But anyway, what would happen is you would react. Well, an equation does the exact same thing. So in this problem, there was H2 added. In order for the system to come back to equilibrium, what happened is it had to undergo what is called a right shift. That meant we were going to make more NH3, and if you look, you see NH3 did increase, and when we shifted to the right, we would decrease the amount of H2, and we could decrease the amount of N2. When all was said and done, we still have the exact same K. That is how simple this is. Let's take it a little bit further. Normally, I would do a demo in class. I would have a clear solution of an iron 3 cation and a clear solution of a thiocyanate anion. I would add different chemicals, and you would say to me, what's the color change? When these two materials come together, they make a complex, iron SCN2+, and it has a kind of a rusty color. I hope to be able to show the video when we're doing our lecture Zoom. So think about what happened with the ammonia. If I add either Fe3+, which is a reactant, or SCN-, which is a reactant, I, by Le Chatelier's principle, would say to you, I'm going to shift right. Well, you know what? If we were in class, we would see color to the solution. So much better live than trying to convince you here. What about these other things? Well, these two go as a pair, sort of. If I add some Ag+, it wants to react with the thiocyanate anion, and it is going to compete. When that happened, what we would see is we would see a shift to the left because we would see less color in our solution. Kind of hard to do right here. Same thing with the F-. The F- would compete with the Fe3+. Since it would compete, there would be a shift to the left and there would be less color. So I'll play it again during the lecture Zoom, but I'm not going to try to work it in here. What about the SO3 2-? Well, that's chemistry that's going to take place, and actually what's going to happen is a redox reaction. The SO3 2- is going to react with the Fe3+, and in the process, it is going to undergo a redox reaction to make Fe2+ and SO4 2-. So we would also see a change in color. Each of these involves a shift to the left. Now again, it's a gorgeous lecture demo. No, you're not expected to do something like this on the midterm. But you notice here, if I would add something that's a reactant, I would shift to the right. If I would add something, or something that competes is a better way to put it, with the product, I would be shifting to the left. And that's summarized on the next slide conceptually, okay? If the concentrations were measured and we did the experiment, we would find that the K is maintained. So you learned about K, you learned about Q. So you need to teach yourself by practicing different problems how to predict the direction, shift, and what's going to be the effect on concentration. So these two go together. If I increase the reactant or I decrease the product, I'm going to see a shift to the right. If I was doing the math and I was crunching numbers, I would find Q is less than K. And again, I would draw my arrow into that point and I would see again a right shift. The third and the fourth go together. If I were to decrease the amount of reactant or increase the amount of product, I would see a shift to the left. Mathematically speaking, if I draw an arrow into the inequality, if I crunch some numbers, I would see a shift to the left. We're going to be doing this in Chapter 17. Here's what the concept is. The important take-home message is we will re-establish equilibrium. Think back to the kinetics chapter. The rates for the forward and the reverse, they're going to be equal again, and that KC is satisfied. I know, I got a C in Gen Chem, so when I have to come back and teach this, all of these things were show me, show me, show me. And I so wish that we could go in the lab and work this out. It'd be very painstaking, but it would show that this concept actually is applied. So the last piece in this section is a lab that I believe you will do. You can have a pink solution of a cobalt +2 ion. If you drop acid, HCl, what will happen is you will then form a blue solution of cobalt. It still remains as a +2 ion. What you just have are different ligands. Here we have the aqua ligand, here we have the chloroligand, and we'll talk about this in Chapter 23. But think about the first one. If I add some HCl, what happens to the color? Well, HCl is a reactant. It says that I should do a shift to the right and the color should become more blue. I do believe you're going to do this in lab this semester. If I add more water, we do it gradually when you do your lab experiment. I'm going to let you think about what's happening. Water sits in the product slot, so therefore the shift is probably going to go to the left, and we will see the appearance of the color pink, but it will go through a violet first, okay? So I'm going to leave that up to you. In your textbook is a big section about temperature, and I'm going to cover that in the next video, but this reaction is an endothermic reaction. What I'll teach in the next video is how you should put heat for an endothermic reaction as a reactant, and you can use the same rules to predict the shift. That is okay, but what will happen is K is going to change. So we'll move on to the next video.